All right, welcome to a pre-recorded lecture. Presumably our last one, although I think I said that in the last one we did. That we actually did, right? There was a promise of one that never happened, but this time, this is for real happening. I am recording. I've got my untitled notebook, apparently. I didn't actually change the name. Look at that. Exciting. All right, yeah, here we go. So here's what we would have done in class tomorrow, more or less. All right, and yeah, so we're going to hit up two things today. So first of all, we're going to finish up everything out of 3.2 that I want to talk about. There are a couple of other things at 3.2 that I don't think we really need to get into, but I definitely want to talk about Schwarz's lemma because it's a nice little application of the maximum modulus principle. So again, we took the time to prove that thing, so let's use it for something. And what's nice is that with Schwarz's lemma in hand, we actually can talk about a very famous theorem and a little bit of complex variable history. So we'll take a little detour there. And then we will start moving into 3.3. So the last things we're going to cover in this class, 3.3 and 3.4, are going to be devoted to basically studying mappings that behave nicely in terms of images, I guess, is the way to say it. We'll see a little bit more as we go. And we've kind of touched on this recently, and more on that when we get there. Okay. All right, so that's the plot for this pre-recorded video. All right, so let's get to it. All right, so what is Schwarz's lemma? That's what we're going to start off with. So let's suppose we got some stuff. Okay. All right, suppose I've got a function. Let's go, ooh, fancy. F that is analytic. Try and use up all these cool colors that I have access to. And we know it's analytic on the open unit circle, such that two things go down. So specifically, we know that f of 0 is 0. And we know that the modulus of f of z is less than or equal to 1. Okay. And again, this is good for... why is the erase turning on? For all of the inputs that we're caring about right now. So we're analytic, and we're only looking at the absolute value of z being strictly less than 1. Okay. All right, so suppose you got this setup. You have your function. Ooh, I get more colors. Yeah. All right, and we got these two conditions going down. My dog is sneezing. That's what you're... Oh my god, are you okay? Okay. All right. Okay. So we have our nice analytic function. We're hanging out on the open unit circle. We know we send 0 to 0, and everywhere in the open unit circle, we are less than 1 in modulus. So let's say you have those conditions. What ends up happening? Well, what ends up happening is something pretty cool. So check this out. Oh my god, what are you doing? Get out of here. So, the trick now is to look at the following. So take our function f and divide it by z. Okay. Right. Now, note, this function right here needs to be analytic. Okay, and why is that true? Well, note our f, since we are analytic, has to be, a power series. And we could center it at 0. But we know that since f of 0 is equal to 0, that means the constant term there does not exist. So our function looks like a1z plus a2z squared plus a3z cubed. So we can divide up the z, and as we've discussed, that ensures that the function that I have here, and we've pulled this trick off before, must actually be analytic. We can actually define 0 divided by 0, in this case to be whatever a1's equal to. All right. So we've pulled this trick before, and this is definitely a very common trick with analytic functions where You can kind of always force them to send 0 to 0. You kind of just have to do a little translation. More on that later. And then the sort of natural, like, oh, well, if I know 0 is 0 and I know I have a power series, well, clearly I want to divide the z out. So, hey, we do that. And now the power of why we have the modulus of f of z less than or equal to 1 comes into view, right? That hypothesis might at first glance be a weird one of like, okay, why would you ever throw that in? Well, check it out. Here's what happens now. So for any complex number whose modulus is r, where r here has to be hanging out between 0 and 1. So visually, what's going on? So we're focusing on the circle, open unit circle. Right, so you got 1, and then we're looking at this. And now we're going, all right, we'll pick an r and look at everything on that circle. So if I look at the modulus of g of z, for any z satisfying this, all right, I'll pick up modulus of f of z divided by the modulus of z. All right, well, the bottom, we know, is equal to r, so I get that. And f of z, our hypothesis, if we let your mind float back, we know that has to be less than or equal to 1. So we got this beautiful little expression right here, that my g of z needs to be less than or equal to 1 over r, and that's good for all r between 0 and 1. So since that's good for every r between 0 and 1, we're going to obviously take a limit, but first things first, let's note something. And I'll squeeze that in right here. So since z is equal to r in modulus, we don't have to worry about anything goofy happening in the denominator with an inequality, because in the top we have the inequality with that less than 1, and if this is equal to r, then we don't have to worry. But note, this actually must be good for all z, even if z's modulus is less than r. Doesn't need to actually be equal. And why is that? Well, on the circle right here, so if we go right here and look at this circle again, I'm drawing over very perfectly. If we look at that circle again, we know that on the boundary of the circle, my analytic function is always less than or equal to 1 over r. And by the maximal modulus principle, we know that that means everywhere inside, it also must be less than or equal to 1 over r. And this is a really powerful fact of the maximal modulus principle, which we didn't explicitly note last time, because last time what we did was prove it and talk a little bit about some things that I've used it for. But right, this is really powerful, because this tells me that I only need to care about what my analytic functions are doing on the boundary of sets. Right, because on the inside of it, it turns out that the inside doesn't matter. The boundary is where all the fun happens. So if I know things work on the boundary, then I know they work inside of the set as well. It's one of the powers of the max mod principle, and here we see it full display. Pretty cool. All right. Nice. So because of this now, we know that g of z is less than or equal to 1 over r, and that's good for all z that are less than or equal to r, not just equal to r. So by taking a limit, are going to 1, and if you want to be really precise with this, it's coming in from the left. We must have that g of z is also less than or equal to 1 for all z strictly less than 1. Note the strict here is needed because we don't know if z we don't have z defined on z with modulus 1. But here this is definitely less than or equal to. But recall that g of z is f of z over z. So multiplying the z over in modulus then gives us the following fact. F of z is always less than or equal to z, and that's good for all z less than 1. And there we go. That is the content of Schwarz's lemma. Ooh. Knowing that you're less than 1 in modulus in the circle ensures that you're always less than z in modulus. Exciting stuff, right? I know. All right, so again, this is a nice little result. It's a really slick little application of the max mod principle. It gives you a flavor of how the max mod kind of gets used. This sort of trick of figure out what's happening on the boundary, and then that tells me what's happening inside of the set. So boundary values being important. Oh man, if you've taken differential equations, maybe you know what I'm talking about. Well, not different, PDEs specifically. So if you've taken Math 385 here at Iowa State. So yeah, that's a neat little idea. And you can abstractify that and push it further. Go ahead and Google Shilov boundary and have a good time figuring out what the hell's going on. And then Google Choquet boundary and have an even more fun time trying to figure out what's going on. Choquet boundary, so while I'm talking about that, let me side note here. So Shilov is spelled like that. Choquet is spelled like this. Choquet boundaries are, so these are things kind of mildly related to the max mod principle. They're interesting things. Choquet boundary is actually a fun one for me personally for a variety of reasons, but my first paper that I ever wrote, we used the Choquet boundary for a couple of things. And my grandmother wanted to see my first paper that I ever published, and so she wanted to read it. And so she was like sitting down and reading it, and then she got to a spot and said, "Christopher, what is a Choquet boundary?" And then I went, "Oh, Grandma, you know what that is. The extreme points of the unit ball of the dual space. Come on. It's first grade. Come on, everyone knows this." All right. Anyway, okay, so we've proven Schwarz's lemma. We got a nice little application of the max mod. Gives a little flavor of how you would use it. Now, this actual result, what can we do with it? Right, because the actual result, the statement of it is like, okay, under these hypotheses, we get that f of z is less than or equal to z. Okay, great. What does that do? What do we do with this? Right. Well, there are things that can be done with this, and depending on whether or not we get to the Riemann mapping theorem, which I don't think we're going to at this rate, there's some stuff. But while we're here, it is worth noting that equipped with this, we actually know something else about our function. So, note well. This tells me that f of z over z in modulus is less than or equal to 1, and let me rewrite that as follows. Z minus 0 in the bottom, and f of z, what do we know f of 0 is? By hypothesis, it was 0. Oh, hey, that difference quotient is less than or equal to 1 in modulus, so I know the modulus of the derivative at 0 has to be less than or equal to 1 always. That's a fun little consequence, and let's push that further. So, note more. My function, remember, is analytic, so it looks like this. Note, our hypothesis ensured that a of 0 was equal to 0. And since I now know that the derivative at 0 is less than 1 in modulus, well, what would the derivative of my function look like? Okay, my derivative... of course, would be a1 plus 2a2z plus some junk, plug in 0. We get a1, and now I know that, oh, hey, the modulus of a1 is less than or equal to 1. Now, equipped with that nice little statement, let's recontextualize this. This says a naught is less than or equal to 0. In modulus, it's equal, obviously, but, oh, hey, look, a0 less than 0, a1 less than 1, There's a completely ridiculous conjecture to make based off the 2 data points. Is it true that the coefficients are always less than or equal to n? This particular question, the answer in general is no, but if you throw in the following, so if you further assume 1 to 1, so if we assume our function is injective, then the answer is yes. Which is very exciting, and that's kind of an interesting thing. So this is known as Debranges. I don't know the right name. I always forget how to pronounce this dude's name. Debranges theorem. And like I said, a brief little fun history fact here. So this is now known as this particular theorem. However, before it was proven, which was in 85, so 1985, pretty recent, I'm almost alive. Not quite yet, but close. It was conjectured in 1916, and here's where we've already made some jokes about this, but it was for a while known as the Bieberbach conjecture. And good old Bieberbach was a straight-up Nazi. Yay! So there you go, another connection to the Third Reich and the complex variables. Yay. So again, of course, our favorite joke, which I will not record, but we said it in class. When I took this class, we took like a whole 20 minutes to talk about this. About how much of a Nazi Bieberbach is. So if you do go to Bieberbach's Wikipedia page, it's like he was a German mathematician and a Nazi. Like it's on the same level. Oh boy. But anyway, I guess Bieberbach kind of noticed that neat little thing with A1 and A0 and went, does that always work? So Bieberbach himself actually showed that A2 is going to work. So initially he figured out that 2 works under the further assumption of injective, and then he wanted to know, well, does it always work? Well, there's 3 data points, obviously it works all the time. And it eventually did get figured out, which is a neat little result, because again, it's kind of a strange little inequality. Right, you wouldn't really fully expect maybe something like that to be true, but it is. And yeah. There's your little slice of complex variable history. Right? It's very creative, the world of complex variables. And note, again, timeline-wise, pretty recent stuff here in the terms of the pantheon of mathematics. I mean, especially 1985, like I said, that's almost as old as me. It's only a year older, so good stuff. All right, cool. All right, nice. So like I said, this is a brief little application of the Max-Mod principle, a little taste of complex variable history. We might get to using Schwartz lemma when we start talking maybe the Riemann mapping theorem, like I was hoping, but I don't think we're going to get there. I think we'll get to conformal mappings and call it a day. Speaking of conformal mappings, we kind of already started planting the seeds for what that's about. So let's follow that thread a little further here and move our way into 3.3. Okay, so. All right. Next goal. Okay, and essentially our final goal for the course. We want to investigate images of analytic functions where A is a nice subset of the complex plane C. Now recall, we already know something really nice about analytic functions, that they take open sets and map them to open sets. So that was the content of the open mapping theorem, and we use that to prove the Max-Mod principle, which we now just use to prove Schwarz's lemma, right? Which is, that's the goal of math, right? I prove this, now I'm going to use it to prove something else. And it's proofs all the way down. All right. So we now want to investigate this a little bit more. So obviously open sets going to open sets is quite nice, but something we want to now look at is, all right, well, we know analytic functions do that, but do they do things even nicer? Like, let's say, do they take, oh, I don't know, a line and turn a line into a line? Or do they take circles and keep them circles? Ooh. So we want to address those sorts of questions. So we now know that open goes to open, but what about, like, shape? Right? Do squares go to squares or something like that? Well, it turns out that it's pretty easy to cook up analytic functions that kind of scramble how shapes look. So, for example, feed a straight line into sine, I mean, you're not getting a line back. But it turns out that we can predict a lot of what's going to happen, and certain shapes are going to go to other shapes quite nicely, and that's effectively what we're going to get to when we talk conformal mappings. But before we get there, we're going to take the time to look at two specific type of functions today, and then in class on Tuesday we're going to combine them together and see what they do. And yeah, that's exactly what we are doing. Okay. All right, so let's start off with some pretty nice looking functions, and let's keep it simple. Okay. So, first, let's look at the second easiest possible type of analytic function. Obviously, we could look at constants, but those aren't particularly interesting. Let's look at these. So we'll call these complex linear. Functions. And that might be an abuse of words there, because if you said that to, depending on who you said that to, they might think of a different thing. But for us, we'll look at this, and the A, of course, we will go ahead and say that's non-zero. Obviously, if A is 0, then this is quite boring. So note something about this. If I factor out my A, and I factor out its modulus, I can rewrite my function as follows. Modulus of A divided by its modulus, Z plus B. All right, now at first glance, you might look at that and go, yeah, sure, you could do that, but okay. Well, note something. There are now 3 distinct things that happen to my input as my function spits out the output. Z goes in, Z gets multiplied by this complex number, then Z gets multiplied by this real number, and then we add this complex one. And all 3 of these together will describe the behavior of AZ plus B completely. And, of course, each one of these individual things are going to actually correspond to some nice geometric stuff. So, first of all, A over its modulus here, this, as we're going to see, is a rotation. Multiplying by this real number is a magnification. And adding a complex number is simply a translation. So, in other words, we know exactly what this function is going to do to any point in the plane, and thus we know what it's going to do for any subset. It will always rotate, magnify, and translate, and note it's going to do it exactly in that order. Because give me an input, it will rotate, it will magnify, it will translate, exactly like that. So let's justify that all of these things are exactly what I'm saying that they're doing, that this is actually indeed a rotation, that this is indeed a magnification, and that this is indeed a translation. And then we'll investigate what a function does to a specific shape, and we'll have a good time. Okay, so first, let's justify the rotation part. Okay, so take a complex number of modulus 1. Okay. Then, if I look at W times Z, all right, now putting everything into its polar exponential form, since W is on the unit circle, we know it's e to the I t for some t. Z can be put into its polar form as well, e to the I theta like that. And multiplying them out gives me r e to the I theta plus t. So indeed, if I think about my points here in the plane, so if I were to draw this out, so my z looks like that, and then now once I've multiplied it by w, note the r stays the same, so my new w times z. So the length there from the origin, so wz, is still on r, but now the angle has just been increased by a factor of t, whatever the t may have been. Oh my god, it looks terrible in there. Little eraser. Okay. Right, we're here. I've got my theta plus t. Beautiful. So, indeed, multiplying by a complex number of modulus 1 does just rotate. Right, here we see it in polar form being explicitly done. Cool. All right. All right, what color to use for mag? I gotta use red. All right, magnification. So if you take a real number and you look at r times z, all right, well, z, again, in its polar form, let's say it's rho e to the I theta, well, r times rho e to the I theta, so the angle stays the same, but how far away has been magnified by r. So indeed, multiplying by a real number magnifies. So if we were hanging out, here's my z, and again, there's an r and a theta. Multiplying by r will just, that right there is rho, and then multiplying by it will create rz, which will stay on the same line, have the same angle, but now has just been modified. Okay, and note real number here positive, right? Because if we let our minds float back to what we're doing, that was a strictly positive real number. So note, if r was negative, then our angle would actually change because we'd be on the, we wouldn't stay in whatever quadrant we were. It would shoot us for the origin, but we're magnifying strictly with r here, so positive, so we don't have to worry about any goofy things happening with the minus sign shooting us through. All right, nice. Beautiful. All right. And finally, so we've justified the rotation part, the magnification part. Now let's justify the translation part. And that one is super easy. To see, because if we are adding a complex number b, that's s plus it. And if I look at my complex number z, which is a plus bi, z plus b, s plus a plus t plus bi. So the real part gets shifted by s, and the imaginary part gets shifted by t, so it's clearly translating. Obviously, a translation is going down. Because if we've got our complex number here, which is a plus bi, well, then adding s to so real part A, there is a plus s, complex part B, t plus b, so yeah, simply just push it however far it needs to go in both the x and y directions. So, yeah. All right. So equipped with all of that, I can now look at any function of that form and tell you exactly what it's going to do to certain shapes. So let's get an example.